Welcome to your tutorial on correlation and regression. First, we'll look at checking the assumptions of correlation and regression. Okay, so the first thing we're going to do is test the assumptions of both the correlation and regression analysis. So if you recall, the only two that are really important for this course are that we have two variables that are measured at the interval and ratio level so that they're continuous. And that we have a linear relationship between the two variables. So today we're looking at two different test scores in a class, and these were measured out of 10. And we can see that students were able to get kind of any kind of score between 0 and 10. So this would be similar to a ratio level, or would be a ratio level variable for both of these. So what we want to do is first just kind of visually inspect the data to make sure that we have a linear relationship. So as you might recall, the way we would do this is just through the charts option, and we click on scatter dot. So that's the appropriate chart when we're looking at two continuous variables. And in this case, it doesn't matter which one's on the x-axis or the y-axis because we just want to make sure that there's a linear relationship between the two. And the only thing that'll change is kind of the direction of the linear relationship, depending on which one you put where. So if we put, one here and two, it might look like this. If we were to flip them, it might, it'll look basically inverted. So that's fine. So we'll put test one there, test two here, and click OK, and we'll get our results. And what we're essentially looking for is just something that's not obviously a nonlinear shape. So like a cloud like this is fine. We can see that there's a few kind of scores, like lower scores here. But generally speaking, this type of cloud suggests that this relationship between the two variables isn't particularly strong, but we're not seeing something that's nonlinear. So we're not seeing like an S, or an arc, like a parable, or an exponential relationship where kind of it gets starts weaker and gets stronger. So as long as you don't see something that's clearly not linear, you're okay to proceed. So in this case, we're fine. So and actually, just before, if you see something where you have kind of like a cluster of scores here and a cluster of scores there, that just means that there aren't a lot of scores in the middle of the two variables that you have, but it's still generally linear as long as it's going up there, right? If they were like here and here, that would suggest maybe not as much. All right, so we'll close that, and that concludes checking the assumptions. Now we'll cover how to run a correlation analysis. Okay, so to run the correlation analysis, we're going to look and see if there's a relationship between how students scored on test one and how they scored on test two. So if you recall, with a correlation, we're looking at the relationship between two continuous variables. But in this case, it's not really important which one is the independent variable or dependent variable, because we're assuming that there isn't one. We're just looking at whether these two variables are related to each other. So that means that if someone has a low score on one variable, they're more likely to have a low score on the other. And if they have a high score on one, then a high score on the other. So that would be a positive relationship, or a negative relationship where low score on one variable means a high score on the other, and a high score on the one means a low score on the other. So we just want to see if that is happening. So to test the correlation, what we're going to do is go to Analyze and Correlate, and then pick between these options. So the one that we've seen in class falls under the bivariate correlation. These are just some other options, but just need to look at this one. So you click on bivariate, and you can see this window opens here, and you have your list of variables on this side, and then you're going to put the ones that you want to look at on this side. So what's interesting about a correlation is that you could run basically all the variables in your data set at the same time, and it's just going to create a giant table. And this is usually a good thing to do as an exploratory analysis before you get going into your data, just to kind of look and see whether things that you expected to be related to each other are related to each other. As a reminder, of course, this refers to continuous variables only. And then right under here, we can see that there's different correlation coefficients. So again, the one that we saw in our class is Pearson correlation. And you might recall that one of the other assumptions I talked to you about that we didn't really get into is that the data has to be normally distributed. So that means that if you recall, our normal distribution has that kind of bell-shaped curve. So we're looking for that in both variables that we're interested in looking at. If for whatever reason, though, we don't meet that assumption, there's other types of correlations that we can run, and these are called non-parametric tests. And we'll basically make an adjustment for the fact that we don't have normal data. And what's also interesting is that these analyses can also handle having ordinal data. So not nominal data, but if you recall, ordinal data is data that can be, it's categorical, but can be placed in a kind of universal order. So there are ways in certain circumstances to run correlations on that kind of data, but that's just more for your info. For this class, just pretend that the only one you can do is the Pearson correlation, which means that you need interval and ratio data. And another thing here that you have the option of examining is whether you want to have a two-tailed or a one-tailed analysis. So we've been working all semester on the assumption of just looking at two-tailed analyses, which means that we aren't proposing whether or not we expect to see kind of a positive or a negative relationship, but just looking to see what the relationship is. If we had a reason, to think that the relationship should be in a certain direction, you could do a one-tailed. So what it does is it shifts that 5% probability, or that we were looking at. So keeping in mind, we want to have 95% certainty that the results we're seeing are not due to chance. And that's automatically in kind of both sides of the distribution, but you can shift it so that 5% is on one side and none is on this side. But again, that's something you need to worry about for this course. And then finally here, you can ask SPSS to actually flag the significant correlations, and it'll do this with just a little asterisk. So that means that if the probability is less than 0.05, it'll just flag it for you. So when you're looking at a little table, that's not a big deal, but if you were to run a whole bunch of variables at once, this is a handy thing. So what we're going to do is just move our two variables that we're interested in over. And then on the options side, you can see here that there's the option to have the means and standard deviations of both variables, as well as the cross product deviations and covariances. So this is part of what I showed you to calculate in class. And then you have the option of selecting whether variables want to be excluded, or missing variables want to be excluded pairwise or listwise. So when you're only running one pair, this doesn't matter. But if you had a whole bunch of variables, if you do pairwise exclusion, it means that if someone's missing a data point on test one, but has all the other data, their data will be included in all the analyses it can do. However, if you were to select listwise, it would mean that anyone with missing data on any of the variables in here is going to be excluded from everything. So typically people, to try to conserve the biggest number of participants possible, the default is to just leave it on pairwise. Style, there's nothing you need to do here, and bootstrap, nothing you need to do here as well. So basically all you need to do is move these over, and that is it. So you click OK, it's going to run the analysis. And essentially we get a table like this. So it's important to note that this table, if you have more variables, is just going to get bigger this way, but also bigger this way. And everything on top of the middle line here, like this middle diagonal, is the opposite of what's below it. So I'm going to show you an example in a second by just throwing the ID variable in here as well, so you can see how the table just gets bigger. Okay, so what's important to note is that this first cell here represents the correlation between test one with itself. So you'll notice here it has the value of 1, and that is because it's perfectly correlated to itself. So there isn't even a probability associated with it because it's perfect. And then here n is the number of participants. And then the next cell over, we can see test 2 with test 1. So here we have the correlation value, which is 0.323. We have the exact probability here, and we have the participants. And as you can see right here with these asterisks, it means that the correlation was significant at the 0.01 level. Okay, so that means that the probability is quite small. And if you were to double click on that probability value here, you can just see exactly how small it is. So I'm going to close that, And I'm just going to show you how the table gets bigger if we actually add additional variables. So ID is a nonsensical variable in the sense that it's just a participant's ID. However, it'll still run it if you let it. Um, and we can see here that it doesn't it doesn't have a relationship with either test. But what we can see is that by adding another variable, the table just got bigger. So as you can see, this is the opposite of what you see down here. This is opposite of that. This is opposite of that. And then through the diagonal is each variable correlated with itself. And it always has that perfect correlation. And one last thing I forgot to show you is how to get the R-square value when you run a correlation analysis. So as you can see here, the value isn't in the output and it wasn't possible to select it in the analysis properties. So what you would need to do is just do it manually. So if you recall, the Pearson correlation value is an R. And to get the R square, you just need to square it. So you would do 0.323 times 0.323, and that would get you your R square value of 0.10, or 10% of the variance in test 1 is related to the variance in test 2. And finally, we will now talk about how to run and interpret a regression analysis. Okay, so now let's pretend that we wanted to see if the scores on test 1 predicted the scores on test 2 for students. So I will, as a reminder here, just warn you against using the term predicted liberally. Essentially, a lot of the research we do in a social science are ultimately correlational analyses, even though we sometimes will use regressions and other more advanced techniques to look at variables. But ultimately, unless your research design as a randomized controlled trial with an experimental group and a control group, and kind of random chance of being in either group, it's kind of hard to use the word predicted. So even if you run in a regression, we typically tend to still just stick with using related, etc. But for this class, if we say predicted, you can run the regression. So, so what we would do in this case is we go on to analyze regression. And there's a lot of different options, and this just has to do with kind of like what type of data you're dealing with. But in the case of two variables where the independent variable is continuous and the dependent variable is continuous, and we're looking at that linear relationship between the two, we would just click on linear. So this opens kind of a more fancy dialog box. And so what we're interested in is whether test 1 predicts test 2. And so as you can see here, you can enter one variable as the dependent. We're going to put test 2 there. And then the independent variable goes here. But you'll notice it says independence with an S, and that is because you can enter multiple different variables. And you can also, if you do decide to enter multiple different variables, you can actually change the way that SPSS analyzes or estimates the relationship between each of those variables with the dependent variable. So that's a more advanced technique that we won't be seeing in this class, but this is where you'd select that. And then you can also have different cases or different criteria to be in the analysis, and you can put this here. But in our case, it's just a simple regression. So that means one independent variable, one dependent variable, both measured at the interval or ratio level, so continuous. So you would just set it up this way. And then on the statistics side, if you open this box here, model fit is going to give us that kind of R square value and tell us how well the data fits the model. In terms of the regression coefficients, if we select estimates here, this is actually going to give us the value for the slope and the intercept. You can also ask it to give you the confidence intervals around those estimates. So that's kind of up to you, but you don't need it for this course. And then if you're interested in kind of the error around your regression line, you have some options here as well, but we're going to leave that for now. And then I didn't actually get through the rest of this, but the R-square change is more interested in multiple regression analyses. So that's where you have multiple independent variables. The descriptive statistics, that would just be the descriptive statistics for the variables that we're testing. And then the kind of part and partial correlations and collinearity diagnostics, again, have to do with cases where you have multiple independent variables. So don't worry about that. So we can continue there. Plots, so you do have an option to plot different types of relationships between the independent and dependent variable. And you can also get it to give you estimates of the error and kind of present between the two variables. So we're not going to bother with that, but it's an option. Um, so save here, what it can do is create um, new variables that have the predicted scores that the regression line would be predicting, or the residuals or other variables. But again, we don't need that for this class. Under options, again, this is that same situation with what to do with missing variables. So you have the option of excluding cases listwise or pairwise, but you can also just replace them in the case of regression with the mean score of the variable. So for example, if we're missing someone's test one score, you can just replace it with the mean for the entire class for test one. And then uh, this is not something we need to worry about here. And then finally, style, nothing there, and bootstrap, nothing you need to do here. So essentially, in our case, really, you're just putting test one here, test two here, and then keeping the estimate or the default setup. So we click OK. And what we end up getting here is these four tables. So the first table is a summary of the analysis that you ran. So you can see here, this is the independent variable in the actual table, and then the dependent variable is listed in the notes under it. So we can see test one predicting test two. And then this is kind of just the default assumption, like in terms of method and the rest of what the table should look like for a simple regression. So where we have one variable predicting one other variable. Next here, we have the model summary table. So what we have is the R value, the R square and adjusted R square, and then the standard error of the estimate. So what you might notice is interesting here is that the R is exactly the same correlation we just ran when we looked at the relationship between test one and test two running the correlational analysis. And that is because if you're running a regression with just two variables, there is only that, like it's only measuring the relationship between two. So it ends up being the exact same thing as a correlation. And the R square is the same one that we obtained when I calculated it by hand using the little calculator here. So we have 0.104 or 10% shared variance. An adjusted R square is basically this value accounting for some error. And then this is the standard error of this estimate here. So essentially, you don't need to worry about these last two, and it's really just the R square there that's important. Then you get to the model fit table, so the ANOVA table. And if you recall in class, we saw that um, this here represents how much variance is being explained by the regression line. This is how much error there is around the regression line. And then this is kind of the total amount of error in our data. Then we have the degrees of freedom for the where's my time? Sorry, for the model degrees of freedom for the error, and then total degrees of freedom. And if you recall, it's essentially for a simple regression, the first degrees of freedom is always going to be one, and then the second one is based on your sample size. And then here we have the mean square value, which is this divided by the degrees of freedom, and then this F ratio, which is obtained by dividing this by this. But what's important for you essentially is to just look at the probability rate here and see if this is smaller than 0.05. And if it is, then you can conclude that your regression line fits your data well and that you have a significant relationship or linear relationship between the independent variable and the dependent variable. And the information that you're reporting from this table is the F for 1 and 329 degrees of freedom, and the F is equal to 38.20. And then that significance value here, which you would write down as P is smaller than 0.001. And sorry, from this table, you would take that R square value. And then finally, this last table here lets us look a little bit more at exactly what's happening. So we have, if you recall, the intercept values are on the first row, and then the slope value is on the second row. We can see based on these significance values here that both of these numbers, so 5.524 and 0.182, are different enough from 0 to be meaningful. Um, if you recall from the class lecture, this value here, it doesn't matter if the constant is different than 0 or not. But the slope needs to be. Otherwise, it means that we kind of have a flat line between the two, and that the best predictor of the dependent variable is just the mean of the dependent variable. So what we can see here is that um, if um, if test score is equal, if test 2 is equal to, oh, sorry, I lied. If test 1 is equal to 0, so if x is 0, then the score of y would be 5.52. So that would be where the regression line starts, kind of at the y-axis is at 5, right? Like, so if it was here, it'd be like up there. And then we can see that for every 1 unit increase in test 1, test 2 goes up 0.182. Okay, so it's not a really strong relationship in terms of how much better if you do on test 1, how much of a difference it makes on test 2, but we do still have that significant linear relationship between the two. These are just the standard errors of those estimates. And then finally here we have the standardized coefficient, which again, in the case of a simple regression, this value ends up also being the same as the correlation. But standardized coefficients become interesting and important when you have a multiple regression and lots of different predictors, because this lets you compare each of the predictors in the same unit of measurement to see which one has the strongest relationship with the dependent variable. And in that case, it wouldn't be equal to the R value that you'd see because it would be looking at a bunch of different values at the same time. But when you're just running simple regression, that correlation comes up a couple times. So that is how you would interpret all of this. And from this last table, the values that you would be reporting would be the value of the unstandardized beta right here, so 0.818, and then you would also report the t and the probability for that beta. So that covers how to do a simple regression in SPSS. All right, thank you.